Good, so now we're back at Claude's lectures, where afternoon where he takes us into the world of algebras and full algebras.
Yes. Okay, so this is the blackboard where we stopped this morning. Are there questions about the things I did on the blackboard this morning's lecture? Okay, so the first thing we're going to do is we're going to equip A with an algebra structure. In particular, in some sense, this is already, I defined it as containing all products. But what we will see is that there's a very natural way to multiply polygons. In the sense that you take two polygons, you multiply them, you get back a linear combination of polygons without products. And so to see that, let's go and consider order of the two polygons of weight 1. This, I remind you, if you look at the formulas in this morning's lecture, is the order of the two logs. So I just want to multiply these two logs. And I put the logs in brackets because I want to think of them as g's, as multiple polygons. Okay, so what can I do? Well, let's spell out the integral definition. And for simplicity, let me say A and B are not 0. That is the first guy. Let's take the second guy. Okay. So just insert the definition. Note that I look at the kind of special case to say that the endpoints are the same. This will be important. So, well, I guess we all know that this, I could also write it as the integral over some square right? It's the same thing. So let's make a picture of that. Say this is Z. This is Z. And so my integration region is this square. Now, let me go and split the square into two triangles. One triangle is the lower one. And the other triangle is the upper triangle. So I can split this one double integral into a sum of double integrals over two triangles. Okay, so let's start with the red triangle. The red triangle, so this is T1 and this is T2. The red triangle, T1 goes from 0 to 0. T2, if I fix T1, goes from 0 to T1. Okay? That's the red part. Now, you can easily check that the blue guy will be the same, except that I have to exchange what I call T1 and T2. So now, T2 goes from 0 to Z, and T1 goes from 0 to T2. That's the blue part. And, well, that guy, you see, is actually just this integral evaluated at T1. And then if you compare it to the definition of a multiple polylog, you see that the red guy is just G, A, B, Z. And the other integral is just G, B, A, Z. Okay? So what I observe is that if I multiply two polylogs of weight 1, which is the same last argument, I get back the sum of multiple polylogs of weight 2 with the same argument at the end, wherever the arguments have been commuted around. And I guess it does not need too much imagination to see that that will always happen. If I have now 3 of these guys, or say I have weight 1 times weight 2, I go to 3-dimensional space, I triangulate everything into simplices, I have to rearrange them, and then I just get some permutation of the original arguments. Okay? Such an algebra, so this of course defines now an algebra, is called the shuffle algebra. I will not give you the formal definition of the shuffle algebra. There is a mathematical formal way of defining it. It's really what you get out of this operation. And the reason it's called shuffle algebra is because it's the algebra that underlies the shuffling of cards. So this is, you have one deck of cards. One deck has just a single card called A, the other deck has a single card called B. What are the possible ways you can shuffle these two decks? Well, you put either A on top of B or B on top of A. So what is G, A, Z, G, B, C, Z? Well, now you have two decks of cards. One has a single card called A, the other one has two cards called B and C in this order, so B is on top of A. What are the ways you can shuffle them? Well, shuffling means that you're not going to destroy the order between B and C, you're just going to interlace them. So you can put either A on top of B and C, you can put A in between B and C, or you can put A at the very bottom. Okay? And I leave it to you as an exercise to go and work out this guy. Or you can do it at the end of the lecture. Okay? So polylogarithms form a shuffle algebra. This is actually a property of a general thing called iterated integrals, which are these kind of recursive definitions of integrals. Any questions? So, with that, I guess there's one thing which you can immediately see from this analogy with shuffling cards. There's kind of a conserved quantity hiding in there. If you take two decks of cards, the number of cards is obviously conserved in whatever you shuffle them. Okay? If you start out with 25 cards in one deck and 50 in the other deck, you will get decks of with 75 cards. The number of cards in your deck is essentially, that is the weight. That's the number of, well, it's erased, it's the number of integrations. So your shuffle product will preserve the weight. Okay? If you multiply, let's keep this. If you multiply two functions of weight, n1 and n2, you get back a function of n1 plus n2, or linear combination of those. You can write this mathematically. The same if I take an element in my space n1 and multiply it with an element in my space n2, that will actually give me an element in my space n1 plus n2. Okay? That's literally just saying that you take a deck of cards with n1 cards, a deck of cards with n2 cards. Whenever you shuffle them, you will get a deck of cards with n1 plus n2 cards. Behind that actually hides something much, much deeper. Namely, the fact that here we define this as a union, so it's actually filtration. Filtration, who doesn't know what a filtration is? Filtration is a Russian doll. It's things sit in one another. So you have this A3, which contains A2, which contains A1. That's the Russian doll. That is what that does, because I add more and more things to it. So it's like the space gets bigger and bigger, and it only contains the lower one. It actually turns out, and it is highly non-trivial, that this union here can be replaced by a direct sum. A direct sum is like boxes you put next to each other. Okay, they don't overlap. Because remember, what direct sum means is vector spaces. Direct sum means that there's a unique way of decomposing something into two sums. But the boxes don't overlap. There's a unique way of doing the decomposition. So actually, it's really at the same level of conjecture, deep mathematical conjecture, that this is a direct sum. So we'll spend some time explaining what that means and why it is actually very deep. This is a direct sum. So what are the consequences of this? And then we say that the algebra is graded. Graded means that you have these two properties. So what is the consequence of the statement that this is actually not just a union, so I do not just lump together a function of different weight, but the sum is direct. Imagine I give you a linear combination of polygons of weight 2, the sum of dialogues. Can that thing give me just a dot? Can I find linear combination of dialogues such as the result is just a single node? The answer is no, and the reason is the fact that this sum is direct. Because if these direct sums are like orthogonal, right? If I take sums of things that have weight 2, they are orthogonal to things that have weight 1. So I cannot find the sum of things in here that end up here.
Excuse me.
Yeah?
A n belongs to the domains of degree n or less than or equal to?
Weight n, but if you want, if it was, if I have this, I can always define a filtration by just taking the unions of things up to n. If there were a relations that would allow me to say, take sums of weight 2 that gives me weight 1, then I would get a filtration, and n would only be well defined as things up to weight n. The statement is as well defined as saying it's just the things of weight n, and I can forget about everything below, because there can be no crosstalk between different degrees. Yes?
What does graded mean?
Graded means literally that. That is the definition of graded. The fact that this sum is direct. It's a direct sum. A graded algebra is an algebra that is a direct sum of subspaces such that if you take, well, literally that, if you take something out of the subspace n1, something of the subspace n2, you get something in the subspace n1 plus n2. That's a graded algebra. Another consequence of this sum being direct, and you see maybe how deep that is. Yes?
Just a question. If you have something like 1 plus pi, for example,
Yes.
how would you define the degree of that?
Well, 1 plus pi, this lives in A0, because it's on pi.
Yes.
This thing lives in A1. This is something that lives in the sum of A0 plus A1, but there's a unique way of distinguishing them. It's not that I can find another decomposition in A0 and A1. It's unique.
But that is not in the union of the AN, right?
That is in the union in what? That thing is in the union. The union contains all, it's a union of algebra, so it contains all the possible sums as well. It's not just, I mean, it's a normal sum, union. It's not direct.
It's a sum.
In that level, yes, it's a sum, it's
Okay.
the union of all spaces, and of course I take the longer as a vector space. I need to add all possible sums.
Okay.
Because usual union is set theoretically defined, it's something different, right?
Okay, yeah.
Use a different symbol.
Okay, good. Call it a different symbol. That is fine. So, okay, just to tell you how deep that conjecture is, maybe you have heard, maybe you have not heard, that zeta 3 is not, it's known to be irrational, but it's not known if it's actually an algebraic number. It may just be the square root of some number. Okay? So, zeta 3, you know, is irrational. That was shown by Aperi. But we do not know, is it transcendental? Now, that here implies that zeta 3 must be transcendental. Why? Because zeta 3 has weight 3. So it lives in A3. If it was algebraic, it would live in A0. But the two spaces are kind of orthogonal, so that cannot happen. That tells you how deeply conjectural that statement is. It looks innocent because when you do computations, nothing else than this direct sum ever shows up. But I think this example shows you that this is mathematically very deep. Because this implies number theoretically very deep statements.
So that sum is not only for functions but also for constants?
Yeah. For all things that are...
Okay, what about g from 0?
Sorry?
I mean, there are special values for g's, like for instance 0, which is going to be 0, right?
Yeah.
That's not weight, whatever, it's weight.
Be careful. 0 is an exception because these are vector spaces. 0 is in every vector space.
Okay, and every other constant is going to be greater.
Sorry? Yes. 0 is in some sense that's every weight because it's in every single subspace.
Yeah.
Another consequence of this conjecture is, which is implicitly what we already said, you will not find any relations between functions of different weights. There can be no crosstalk between functions of different weights, because they live in orthogonal spaces. And orthogonal is not the right word, because that would require some scalar product. That's, in your mind, think of direct sums as things being orthogonal. So there are no relations with everything else, and also there, when you evaluate like constants for different weights. It's actually just rephrasing the fact that this space is a direct sum, where weight provides a gradient. Yes. Well, it is well defined as a filtration still. Yeah, this I didn't discuss, but it would in general, W is a filtration. The weight is a filtration. I didn't discuss that. As a filtration, it would be well defined. The conjecture that is actually a grading.
I see, but for example, if I take, I don't know, some dialogue and try to manipulate it and write it as a product of 3 logs, then W would assign both 2 and 3 to this.
Sorry? If you do what? If you... I didn't understand that basically.
The dialogue.
Yeah.
And manipulate it in some way.
Mm-hmm.
If I write it as a product of 3 logs.
Yes.
Then W would not be well defined in this.
Yes.
And
Yes.
it's known that this is impossible, or
No, so what you can prove is that it provides a filtration, so that you would never go up in the weight. But you could generate things that have lower weights. Okay? So in principle, it could happen that you have a dialogue that is actually secretly just a log. It evaluates to the same number as a log. That is the way to think about it. It evaluates to the same number as something else. That is what happens up there, right? I would have zeta 3, which just evaluates to the same number, which is a rational number, so which has weight 0. It would not go up, it would go down. That would mean that this would still be well defined as a filtration. Okay? So because it would have the highest guy plus all the ones that are below. That would still be well defined. The conjecture is that provides a grading, and these things are kind of orthogonal to each other. Yes?
There explains on what is defined being related to trivial appearances.
Sorry, can you speak up?
So is there a constraint on what is considered to be a relation? So for instance, I can say 1 equals dialogue over dialogue, but I doubt that would be
1 equals dialogue.
dialogue over dialogue.
So, okay, yes, so what I mean by this is polylogons with algebraic arguments. Maybe I should straight up. Yeah, with algebraic arguments. Nice. So you won't find any, say, linear combinations of products of polygons with algebraic arguments that would not respect the weight. Of course, I can write down log of E equals 1. That, yes, but then the argument is not, it's not an algebraic number. This is a good comment. More questions or comments? So why do I insist so much on the weight? Well, for 2 reasons. One is just, I'm sorry. One is that there is this conjecture, that there are no relations among about 2 different weights, which is very important. If you work with these functions because it tells you that if you have to solve these functions, you cannot kind of add things that accidentally cancel to give you something simpler. And the other reason is that weight has some kind of natural incarnation for loop integrals. And it's actually related to something that we have already seen. Remember that we said this morning that for one loop integrals in 4 dimensions, you don't need more than dialogues. Okay? And we said this morning. So this morning, reminder, for one loop integrals, L equals 1, D equals 4. When I say D equals 4, I always need a vectorization, and I throw away all the terms in order epsilon. There, the most that I can get are logs of algebraic arguments and dialogues. That'll be so small. So in other words, I can now rephrase this that for length 1 loop in 4 dimensions, I can get at most weight 0, weight 1, and weight 2. Yeah? That's just rephrasing what we said this morning. Now, that statement has a generalization, which goes as follows. So, imagine you have an integral which what? Yeah. In some dimension, okay? This could be the not integer, even. If you go to odd dimension, things are a bit different. When we live in even space and dimensions. And I assume, that is because that's what we do here, that AK can be written in terms of amperes. So it actually finds a point in my space A up there, each AK. Okay? At one loop we said polyloops are enough, at 2 loops we said all Albrecht's loops. So I'm here now I'm restricting myself to a subclass, and those give me polyloops. Then, it's an empirical observation. I don't think that there's any kind of understanding of why that happens. The weight of IK is always lesser and is bounded by 2 times the loop number plus essentially k plus k. Note that this implies this immediately. Sorry, it's actually here. D divided by 2, sorry. It's now in 4 dimensions. C 0 divided by 2. This immediately implies this, because I said I'm in 4 dimensions, and therefore away all the higher order terms, so k is 0. I only look up in terms of k x to the power 0. D naught is 4, so we divide by 2, I get 2. L is 1, so I get at most weight 2. This is quite remarkable. I think no one has an understanding of why that happens. But it's true in all cases we know. And we're talking not here just about a handful of things. Here we're talking about a collection of all loop integrals that people have computed since the early days of quantum field theory. So we're talking about thousands of examples. Okay? Yes?
How many theories saturate
That's the next point.
the amount?
That's the next point. That's because that is, of course, the next question. What happens here? Or do we have kind of a grading in this understanding? So, which theory settles the bond is indeed the next question. So, when is the bond separated? There's one case that we know, where again, this is based on empirical evidence of all examples we know. The bond is saturated in some gauge theory, which is n equals 4 super young modes, both planar and non-planar. All examples we know, the bond is set in full dimensions. All examples we know, the bond is saturated. So there, if you take the Feynman, the loop in amplitude, now we have to talk about full amplitude, okay? Because now, if you take an L loop amplitude in n equals 4 super young wells, its weight will always be, every single term in that expression will have, well, let's say, and remove all the infinite divergences of the finite part. The finite part would have weight 2 times L. You can include the divergent part if you get absolute weight minus 1, but do not go there. Again, this is at the level of complexity. The other theory we know, and this seems to happen in all examples, so this is known up to, I guess, by explicit computation. Where do we stand now in this opposite?
7 loops.
7 loops. So we know it for planar. In the planar limits, we know it for 5, so 4 and 5 legs. We know it holds for L all the way to infinity. Because we know exactly the number of loops. We also know that for the number of legs being 6, as Jörg said, it is known for L less than 7, though to be fair, that goes into the derivation as well, right?
Yes. But it can be checked also in the
Yeah, I know.
yes.
It has 7 particles, I guess. 4 or 3, depending on how you want.
4 in both cases, MHV and then MHV.
Okay. Good. And non-planar, well, non-planar is usually much more complicated. There we know it nowadays for 4 particles up to 3 loops, and for 5 particles up to 2 loops. And while 1 loop we know there are more. And that's all.
So 6 and 7 is for every NMHV degree, or?
Yes. Well, here you only have MHV and MHV, the 6 and 7.
MHV and NMHV.
Yeah. Jörg is the expert in that, so.
The 6-point amplitude, the MHV component is not known to 7 loops, the MMHB to 6 loops.
So here it's 7 MHB 6 next. This won't be long until you guys do the next evolution.
Yes, if we get our hands to it.
The other theory that is known to have that property is any constraint supergravity for dimensions, and it's exactly the same. So it also separates about. And there what is known, well, there planar there's no planar for gravity. There the only thing we have is 4. Is actually this. Now, are there other nice theories? Well, QCD definitely not. Pure Young-Mills definitely not, because we know already one loop, the bone is not separated. But even things like, we have examples of superconformal Elegans-2 theories, they don't separate the bones. Ready for external particles. So there seems to be something very special about n equals 4 super Young-Mills and n equals 8 supergravity, also from the mathematical point of view, when you compute higher order terms in terms of expansion, that I think completely eludes our understanding. At least mine. I don't know. Okay. So why am I telling you this? Well, because this puts very, very strong constraints on which functions could possibly appear in your answer. Yeah? So if you remember where we took off yesterday from the question, well, what functions can you get? We went down into periods, then went to polylogs. Well, respect for no one of the carpet, there's other things, but imagine now someone, if you see this, then at least it's natural to conjecture that this holds on for also for 8 loops, 9 loops. And even then, it's more restricted because we know that only certain weights can appear. So you see, these functions are very, very constrained. And hopefully they are constrained to the extent that if someone gives you a basis for your space, maybe you can just write down an ansatz, and then yeah, but first you would need to fix the coefficient in front of the basis functions. But yeah, usually the way you would then fix the coefficients is rather that you would say, well, I know how my amplitudes behave in some collinear limits, in some soft limits, in some regions of phase space. I know there are some like factorization theorems or whatever that tell me some universal behavior to all orders, and maybe that is enough to fix the amplitude completely. That seems to need to be the case here. That is why people could go to such high reports. That's why I said before, it's not, some of this conjecture goes into verifying the conjecture itself, but then a posteriori you can make checks that you see that you need to put the right answers. Even though you use the conjecture to get the result. Yes?
Just a quick question. So when you say that the bound is not saturated in something like the mills, do you mean that you get terms with the maximum weight and below, or that you don't get the top weight? So, like,
both things can happen.
okay.
If you take, for example, the 1 to 2 point function in 4 dimensions, you would expect that that thing is well, this is d equals 4, l equals 1. So the bound should be less or equal to 2. You compute it, you point below. In general, it means that you get the top component and everything below. But then there are really things that are understood. Like I said, there are n equals 2 cases where we know the bound is not separated, but you only get one layer below, not everything below. So there's still some structure to be understood in the lower weight terms, but we don't even understand the theories that separate the bound, the why separate the bound. Not even talking about the fact that here I restricted myself to polylobes. As I said, there's, well, we opened Pandora's box, there's much more out there. And for these other things, we wouldn't even know what that means. But clearly, I think it's enough evidence to know that there's something there. Yes?
If I'm not wrong, you said before that you can also have other stuff other than MDLs.
Yeah.
So this means that for the theories in which the boundary is saturated, you can only have MDLs, and this has been proven that you have nothing else?
No. So it says here, I made the assumption that if that is the case, then my conjecture holds. Now here, I also, in formulating this conjecture of the theory, I make also the assumption that my amplitude to all in orders is polylobes, nothing else. That, I think like here, goes in. Now, we also know that, but there are arguments why certain holistic configurations of MHV, you expect them to be polylobes. I wouldn't call maybe these arguments proofs, but there are good arguments why this should be the case. But we also know that if you go here higher, starting from 10 legs, 2 loops, we know that polylobes are definitely not going to be enough. And what happens then there to that conjecture for the cases where we know we don't get polylobes anymore? I don't know, but also we don't know how to compute it, so we can't check. But it would be an interesting question. Yes?
If I understand correctly, we also have by now maybe at least some idea what weight could be for EMPLs.
Yes.
So is there already such a similar conjecture for EMPLs?
So what you do see for the case 10 where you get elliptic guys, just by looking at the form of the integral, you expect that you also get weight 4.
Okay.
The reason is that there you have, I'm just talking to people now, you get a period, and you get something that has length 4, but has a weight 0, guys. So it has weight 1 plus weight 3, which is still 4. So it looks slightly different, but it still seems to hold. But no one has ever computed that thing through glory, so that is at the level of speculation.
Okay.
Yes?
So does there exist a similar relation for the case of the dots? But this was only for even dimensions.
Presumably there is. Now, the number of data points that we have in odd dimensions is just very, very small. Because 99% of the loop intervals have been computed in 4 dimensions. Now, 4 and even is roughly the same. Because that's not something that is discussed, so we had these relations that connected different powers of operators, the linear relations. There are similar relations that connect integrals in d plus 2, d plus 4, d plus 6. So if you have them all in one even dimensions, you get them all the conclusions also in every even dimension. But all these things go by steps of 2. It's because in all of these things, what enters is always d divided by 2. So things always go in steps of 2. And for odd dimensions, maybe there is such a pattern, but I don't know it because I don't have enough experience. We have not seen enough data points to make the conjecture. It gets even weirder, and then I think we go on. We even have examples that if you take, say, QCD, where you get the bounds and everything below, and if you just look at the terms that saturate the bound, you find n equals for super animals. But we also have examples where that doesn't work, so that seems to be observable dependent. So there's really to be something to be understood here, and we really don't understand. Yeah? But yeah. Yes?
Looking at this band, if I try to naively count how many integrals I need to do to evaluate the Feynman integral for quantum groups, what did I get?
This does not tell you anything about the number. This just tells you something about the class of functions that can show up in the answer.
Yeah, but I started from some rational function and I had it inside the integral and this integral is...
Yeah, but it doesn't. This, for example, would tell you would get dialogues. It would not tell you dialogues of what. It just tells you dialogues of some algebraic function. tells you weight 2, so it tells you dialogues. But there are still infinitely many different arguments I could put into my dialogue. And that depends on the specific integral I'm looking at. Okay? More questions? So, let's think this is a starting point then to discuss the following. So we said, imagine I were to give you a basis of this space of all the functions that can show up, say for 6 points at weight 12. Weight 12 means L equals 6, so that would be here. If I give you a basis of that space, then you could try to write out the numbers and fix the coefficients. I'm jumping over some subtleties, but say it's good to keep that in your mind. The question is, how do you decide that you have found a basis? For example, let me just give you an example to motivate what's coming next. Let's say I would weight 2. Let's say Z is my kinematic variable. I decide that dialog Z is a good argument here for some reason. Well, if I have dialog Z, probably I should also have log Z. So it's weight 2, so I should have log square Z. Maybe I also have log 1 minus Z. That's good. Say for some reason I know that Z and 1 minus Z naturally show up in my calculation. Log square 1 minus Z, if I have log 1 minus Z, I can also multiply it. Well, if I have dialog Z, well then why not dialog of 1 minus Z? And I write down the answers, but now I'm over constrained, because this morning I told you that dialog of 1 minus Z equals minus dialog of Z minus log Z log 1 minus Z plus pi square over 6. So they are related. So how do I decide that I have a basis? Or I can also phrase it, how do I resolve the identities among these functions? Okay? If I know how to resolve the identities, then I can conclude that maybe that guy don't need it. Okay? So that brings me then the next part of the talk, which will also be kind of the last big item, probably, which is about the relations among these functions. And again, keep in mind the example that I gave this morning of the trigonometric functions. Right? This is like giving you sine x, sine y, cosine x, cosine y, sine x plus y. And you need a way to resolve the identities among these trigonometric functions. It's the same with these polygons. Yeah?
In this example you've just given, would you not need to also include pi squared over 6?
Sure. Yeah. But that is a constant, that's why I didn't put it here. That's just to give you an idea of why these things are, why I care about relations. Okay? So, understand that part. I'm going to come to what nowadays you can kind of consider that's like the modern approach polygons, if you want. Is that, so we said so far that our A was vector space, and we said, well, it's an algebra. It's a shuffle product or just multiplication of functions. We said, it's actually graded, so the weight is preserved. It's a direct sum. It turns out that it has even more structure. And its structure is Hopf algebra. Just so I have an idea of how much detail I should go, who in this room knows what a Hopf algebra is? Okay. So, I guess you all know what an algebra is. So who does not know what an algebra is? Good, that's reassuring. So an algebra, I guess you all know as well as vector space is multiplication. Okay? I can see that as well. I have a vector space, which I called A before, but let's be generic. So A, I use the same notation as before because it is, but for now it's just abstract algebra. It's not going to understand. So I have a map that allows me to take two objects and create a new one. So I take A and B, and let me write it as A tensor B. If you don't know what tensor means, it's essentially things will disappear for now. And I return A times B. Right? That is multiplication. You guys will agree on that. An algebra is a vector space that has such a map. Also to take elements and create a new one. It's also supposed to be associative. So associative, I guess you all know what it means. It means that A times B times C is equal to A times B times C. Something also you all know. I can give it another interpretation, which you may be less familiar with, but I think it's very nice to understand what happens when you go to co-algebra or Hopf-algebra later on. So what I've done here is I've started with three elements. So I started in the space, I took 3 copies of A, right? And I multiplied together the first two. M is for multiplication. So I multiply together the first two, but I do nothing, the identity on the third one. Now I get AB times C, that is here. I could also have put the last two together. So I do nothing in the first slot, and I multiply together the last two slots. This also gives me something here. This gives me, I do nothing here, and I multiply together the last two. And now I just multiply them together. And I get an element in A, and this diagram was commuted, meaning whatever way I choose, I must find the same answer here. So the two ways of doing things must be equal. Okay? That's what associative means. Good. So instead of doing this, I'm now going to, so this is an algebra. Now I'm going to define something called co-algebra. It will be the same, except that all my maps and arrows will go in the opposite direction. So now I start from A. So A is a co-algebra. If it comes with a map, well, I take this and I turn the arrow around. So now I have a map that takes one element and gives me back two. So I start from a single element and I get back many. We'll see an example of that in a second. Oh, we know that map delta, and it's called co-product. Co always means go in the other direction. It is also going to be co-associative, meaning I have to take this diagram and revert all the arrows. So now I start, say, here in the lower corner, where I have one element, take one element, and I take these two arrows, I turn them around, now until it's no longer M, it's delta, my co-product. My co-product gives me two objects. And now I'm going to act with the co-product again in the first slot. Right. So I only act with the co-product in the first slot. So I decompose things into 3. I could also have acted with the co-product now in the second slot, here, not touching the first one, and I require that I get the same answer. That is coefficient. What that normally means is you have room to take an object and to break it into pieces, and coercitivity means that, well, once I know how to break an object into 2 pieces, I can iterate that and break it into 3, 4, 5 pieces. And coercitivity means that there's a unique answer I can get, in whatever way I do the breaking into pieces. Yes?
So yeah, I get like all the possible tensor product that give me that result, right?
But I have not told you yet. I have not told you yet what delta is. I just told you a co-algebra is something like that.
Okay.
Now I can put a different co-products.
Actually, my question was like, if I start with a product,
yeah,
I can define them co-products, right?
On the dual,
Yes.
not on the same space. Now we want to say, okay, now we have the same A, it comes with the multiplication and the co-product at the same time. In principle, these 2 things are completely distinct. Okay? So now, you can also define something in the algebra that is essentially both things at the same time. That is, if you want, I have both multiplication and co-multiplication. And some other things that say for now, and they are compatible in the following sense. If I multiply things together, then I break them apart. I could have broken apart the pieces and then multiply them together. So compatibility condition between 2 operations. Here, for those who are not familiar with this, delta gives me tensor products of elements back, right? And the multiplication of the tensor product is just component-wise. Okay? Now, a Hopf algebra is I'm dropping all steps. Okay, those who know what Hopf algebra are know that there's a bit more. And here I'm just defining the things that we need for the lectures, plus something else, some other condition which for us is irrelevant. So, for what I need, I just defined the concepts that we need in the following. If you want to understand what all the things are, there are more axioms, then you can go to the master's lecture, but they are not important for understanding the rest. So, example of a Hopf algebra or bi-algebra, since instead of doing this, I do the same thing. Let me give you the following operation. So I give you, take letters A, B, C, D, And if I give you letters, you can make words. Words, I mean linear combinations. Linear combinations of words, actually. So words, first of all, would be things like A, B, C squared, A, B. That would be a word for me. Just a sequence of letters. And I can also consider linear combinations with those guys, okay? Formal linear combinations. I can also equip that with a shuffle product. Where now I just consider a word as my deck of cards, and the product of two words is the shuffling of the two decks. So I define now things like we had this morning A, and I use this symbol, which in the mark is always the shuffle product. It's the Russian letter sh. They have some from close to relatively correctly, but I was told it's the Russian letter sh. ABC plus BAC plus BCA. You can check this morning at a similar relation with GAZ and GBCZ. So that defines the multiplication. So what is a co-multiplication? A co-multiplication would be, well, let me give you an example. It's also ways of cutting the word. So how can I cut this word without a single letter? Well, just in two trivial ways. I only have one letter, so I can put it on the left or the right. There's no another thing left. If I give you two-letter words, well, I have that. I have that. But now I have another thing, which is this. And I go on like that, okay? For every word, I can define an operation. You can check that definition with that is compatible in this sense.
Why did I stop in the first one? I mean, I could add infinity many ones.
Yes, but correct. But as say, everything is over Q. Q is my base field. I take a vector space over Q. My scalars I can always remove, right? You could add as many ones as you like, but you would not produce any new structure. Also, and that is maybe the more important reason, my delta only takes values in A tensor A in two slots. I could iterate it, yes. But my delta itself has only two slots. Okay, delta takes values goes from A to A tensor A, it only has two slots. Okay? So you can check as an exercise that this, so if I take words, and I put as multiplication to shuffle, and as co-product delta, the delta defined here, that defines mu by algebra. It actually is also a product. Okay? Okay, so I think this is a good place to take a break. So if you have questions, you can ask questions. And then the last lecture, well, I think it's clear where this is going. I showed you the shuffle algebras or Hopper algebras. I showed you this morning, or just before, the products from shuffle algebra. So the natural step is now to ask what is the co-product on polynomials. You think you gave it to us, but actually I'll show you. Any questions?
So the ultimate aim is to create an ansatz based on the polynomial. That's assuming
Can you speak up?
Oh, sorry, so you're trying to make an answer based on FOIL.
Yeah.
But you assume then the coefficients aren't, they don't depend then on rational functions.
No. So that's why I said at some point the street something from the car. So I assume that my coefficients are rational numbers, which is the true for say n equals 4 MHD sector.
So is that being proven that they don't depend on the no rational functions?
N equals 4 MHD sector, again, now it depends what you call proofs. Let's say physicist proof. Yes, because you know that the leading singularities of MHD amplitude are just the MHD3 within a sector. Now, of course, as someone rigorously with all meeting all mathematical standards proven that leading singularities are the only things that can ever show up as the rational vectors. No, we can debate, but you say this is level and you say the leading singularities are the rational prefactors and only one which is 3.
Any other question for the break?
If no other student asks, so yes, I'll wait for students.
Okay, last chance before Jorgos asks this question. Okay, Jorgos.
In fact, it's on behalf of the students, which I'm sure they have very high level, but in case they were shy, what is a transcendental number and what is an algebraic number?
So an algebraic number is a number that, if you take a polynomial with, say, rational numbers as coefficients, a number is algebraic if it is a solution to such a polynomial. Like I is an algebraic number because it's a solution to x plus 1 equals 0. Pi, for example, is not. You can prove that there is no polynomial with rational numbers with coefficients that has pi as a 0. So it's a statement about, again, it's all of these things about being rational and not being rational. Polynomial versus non-polynomial. Things that you can get as algebraic manipulations, meaning algebraic manipulations are the ones that you do to solve these equations, versus things that you cannot get from algebraic manipulations. Okay? Yes?
Can you assert a weight to numbers which are not periods?
Sorry?
Can you assert a weight to numbers which are not periods?
I don't know. Because I don't know.
You have to calculate over the period.
Yeah, so I don't know. I mean, all these things comes, if you go to the mathematical side, goes to algebraic geometry and where everything then, the periods are defined as the coefficients in the comparison isomorphism back in the RAM homologies, which are integrals of rational functions because it's obviously in the world of algebraic geometry, and that's where these things are. These integrals come out as periods in the sense we defined them. But you're really there in the world of algebraic geometry where you're looking at polynomial equations and you have algebraic RAM homology, so you have your differential forms are really forms times some rational functions. And so then naturally the question of what happened, and then the way it comes out naturally from there. Now, how would you define that if you leave that world? I wouldn't know. I'm not saying it cannot be done, no one has done it. I'm just saying that I just wouldn't know how to do it. Yes? Yeah, so the ones that we are looking at, and not that one, is commutative. This of algebra.
And also,
it's not co-commutative.
Oh, it's not co-commutative. Okay. If I take the dual and then
the dual is co-commutative. The dual actually of that guy is slightly described. The dual of this part is just concatenation. This is deconcatenation of words. The dual is multiplication, which is concatenation of words. It just concatenates the words together. That guy gives you something where the dual of that will be something which on letters, well, looks the same, but it's not. That would now act like if you now go to AB. AB in the dual is A concatenated with B in the dual, which is A concatenated with B, which would give you A tensor AB plus A tensor B plus B tensor A plus AB tensor Y. So that is co-commutative, because it came as a dual of something commutative. But now the multiplication is no longer commutative, because this is just concatenation of words, because the co-product it came from was not co-commutative.
Okay, and then my question is, this dual, is it associated with some group?
Yes. Yes. That is a mysterious cosmic Galois group, or typical Galois group, depending on whether you talk about physics or not. It's a Galois group, so the whole thing mathematically is about finding a Galois theory for certain classes of transcendental numbers, namely periods. And this group that is dual to this Hopf algebra is this Galois group.
Okay, so it's just some group which is not...
Well, this is a group which is kind of implicitly defined by its dual, which is this Hopf algebra. So there will be a group that acts on polylogs, this motivi-Galois group. How is it defined? Well, it's defined via its dual, which is defined by its co-product.
Can you write down the name of the group?
So in math, it's called in physics, it's often you find probably maybe a subgroup of that guy. It's called the cosmic. Because that guy acts on all periods. All Feynman integrals are periods, so there's a natural subgroup that will act on Feynman integrals. And here we now really get into the point where, where you're really at the edge of research in both maths and physics. So that is, I think, not even that's even what this group is probably not really clear. Other than that you can define it abstractly via such a construction.
Good. Very urgent question. Let's have a break until 3:45. And then we return for the final lecture.